Hello, everybody. We want to continue the discussion started related to digital signal processing using Python. Now, chapter 1 is started. The goals of chapter 1. Introduction to DSP. The first lesson begins with a reminder of signals and systems. Then DSP systems are introduced. Later, sampling theorem as well as quantization and discrete time convolution are explained. After completing this lesson, you will be able to explain some advantages and disadvantages of DSP systems, describe the effects of changing the sampling frequency, understand the role of anti-aliasing and reconstruction filters. You will also be able to compute linear convolution of two discrete time sequences by hand, as well as computing or calculation in MATLAB or Python or any environment you are interested. But we mainly focus on using Python. In this lecture notes, we will use frequency domain F with dimension hertz and radial frequency domain, that's radian per second, 2 times P times F frequency. We use capital omega for analog signals and frequency domain for digital signals. That's omega equals to capital omega times TS sampling time, and the dimension is radian. You need to be careful. Capital omega radian per second and omega radian. Okay? Instead of each other without a pre-notice unless declared otherwise to have discussion fluently. Okay? So we don't want to repeatedly say frequency or radial frequency. Just be careful. Okay? Now, brief overview of signals and systems. The first one, Fourier Transform of analog or continuous time signals. Here you see the equation necessary for our discussion. Capital X of capital omega is an integration of x of t times e to the power of minus j times capital omega t dt. Okay? And the inverse Fourier transform, you see the equation. You need to write them down carefully for further discussion. All right. Now we'll continue the lecture note. The first important signal. Find the Fourier transform of a pulse in time domain. You know, a pulse in time domain as well as a pulse in frequency domain are very important signals in digital signal processing. Later, we'll be familiar with their application. For instance, we define a pulse in time domain x of t. You see, it has a duration from minus tau over to half tau up to plus half tau. Okay? Using the equation we introduced here, very simple mathematics, you will get another important signal called Sinc. Sinc is sinus alpha over alpha in any domain. Time domain, you are just looking at it, or similarly frequency domain. Okay? Sin alpha over alpha times a constant called tau to compensate the area under the curve. So the nature in frequency domain will be a sinc. Okay, we want to have a look in two signals introduced right now. Pulse in time domain, you see here x of t, everywhere is zero, not unless the duration we have applied for it. But in frequency domain, we are encountering a signal from minus infinity up to plus infinity. Of course, the illustration is concentrated from some point up to some other point. Say it minus 4 up to 4. Okay? Just for illustration. But it is from minus infinity up to plus infinity. This signal has very important characteristics. You see, here the major energy is from, say it somehow from left up to right. Okay? It's called main lobe. The rest are called side lobes. We'll later be more familiar with the idea. For instance, we continue the discussion. Okay. Now we want to design a problem for you as called take home. Find and sketch the inverse Fourier transform that is in time domain of a pulse in frequency domain. Okay? Now this time you have pulse in frequency domain. Find what will be the shape of the signal in time domain using the second equation we introduced earlier in a lecture note. The second question, find and sketch the Fourier transform of an impulse in time domain, not pulse. Pulse has some duration. Impulse, the duration of impulse is 0. The amplitude is infinity. The area under curve is 1. Okay? It will be called impulse or Dirac. The next question, find and sketch the inverse Fourier transform of an impulse in frequency domain. Okay? The earlier one, time domain. The next one, frequency domain.